joy, wisdom, beauty, truth, equality, community, sustainability, and most of all, love. These are the things we live for, and the innovation that really make a difference are the ones that are life enhancing. And that's why the heart of innovation is a desire to re-enchant the world. An idea, a change, or an improvement is only an innovation when it is put to use. And to make it useful, there's a lot of hard work and perseverance. That's what matters. Last year, we made more than 80 research projects, and we plan to make more. We aim to make an even greater, better innovation for Indonesia. The more people committed trying to find a solution, the greater result we can create. Electrical engineering and informatics is about creating something for the future. And that's how we do it. A passion for quality.
Oke. Halo Pak Andrian.
Halo Pak Tutun. Ya ini kelihatannya sudah siap. Dr. Nike sudah ada. Silakan Pak Rahmat atau siapa Pak Tutun dulu.
Akan dibuka dulu apa saya merangkap MC apa gimana? Ada dari Pak Dekan apa?
Langsung aja Pak Asad.
Oh, langsung aja. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Welcome to the lecture on quantum technology, a series by Quantum Technology Lab, STAY. Yeah. And this morning, we will have a lecture on compiling your calculations to run on quantum hardware. I know many of you are aspiring computer scientists, telecommunication engineers, and electronic experts. So hopefully you will find our discussion this morning insightful and inspiring. Before we start the lecture, a little bit about our guest speaker, Dr. Nike Dattani. Dr. Nike Dattani did undergraduate degrees in mathematics, physics, and biology at University of Waterloo in Canada, then a PhD at Oxford University in UK. There he worked on computing Feynman integrals to model quantum dynamics of qubits. And after his PhD, he worked at Kyoto University in Japan, NTU in Singapore, Harvard-Smithsonian Center for Astrophysics in USA, and has many times been a visiting researcher at the Max Planck Institute for Solid-State Research in Germany. He is now the director of HPQC Labs, a high-performance and quantum computing research institute in Waterloo, Canada. Dr. Nike is also known for breaking the world record for largest number factored on a quantum device in 2014. And he's also known for co-inventing the Morse long-range potential energy function and several novel methods for quadratization of higher degree discrete optimization problems into quadratic problems, which are much easier to solve. Without further ado, Dr. Nike Dattani, the time is yours. Hello, Dr. Nike. Okay.
Hello, can people hear me?
Yes, we can hear you clearly.
Okay, can you see my screen?
Yep.
Excellent. Okay.
Yeah.
Thank you very much for the introduction. Terima kasih. Good morning, everyone. Selamat pagi. Thank you very much for the introduction. I'll go into the talk. I want to just start with one slide. How do I get this working? Okay. So I want to just start with one slide showing less than a year ago, I launched this website, the Matter Modeling Stack Exchange, for the modeling of chemistry and physics. So if people are interested in modeling chemistry or physics and they have any questions, this is a great place to get your answers. It's part of the Stack Exchange network. So if you're familiar with Stack Overflow or the Tech Stack Exchange or the Unix and Linux Stack Exchange, this website is part of that network. We have about 2,000 members, 1,000 questions, and more than 1,500 answers in less than a year. Okay, so I'll go on to the next part of my talk where I'm just talking about quantum computing in general. I'm going to start with the Mach-Zehnder experiment that was done in 1891. Now, can people see my cursor? If I put, okay, let's put this.
Yes.
Okay, so I can draw here and you can see what I'm doing. Okay, so if we have a beam of photons going into a beam splitter, this is like a half silvered mirror. So the mirror, this is a mirror where we have put, or it's a piece of glass where we have sprinkled silver on it. So if the photon hits a silver particle, then it will bounce off with the angle of reflection being the silver will cause the photons to reflect off of the mirror and go this way. And because we've only sprinkled the silver 50% on this glass, 50% of the photons will actually go right through, and 50% will go up. Because they've hit a reflective surface. Okay, now this is a full silvered mirror, so 100% of the photons that come here, they're going to reflect. Okay, so 50% of these photons are going to go here, 50% are going to go here, and then we have full silvered mirrors over here where 100% of these photons are going to go here, and 100% of these photons are going to go here. Now we have again a half silvered mirror. Okay, so 50% of these photons are going to go through, and 50% of these photons are going to be reflected. And likewise, for the second mirror, 50% of these photons are going to go right through, and 50% of these photons are going to go reflected. Okay, so I want to ask now, think about this. How many photons do we expect to find at this detector or at this detector? If we have 100% of the photons hitting a half silvered mirror, 50% of them going here, 50% of them going here, then 50% of these ones going here, and 50% of these ones going here, and 50% of these ones going here, and 50% of these ones going here. What do we expect to find at this detector and at this detector? Does anyone know what the answer to this question is? So I can't see the audience. Maybe I'll just draw out that we have 100% here. Let's get a thinner normal size. Okay, 100% of the photons are here. Now we have 50, okay? And then we have 50 here. We go through a full silvered mirror, so all of these photons will land on this half silvered mirror. Half of these photons will land on this half silvered mirror. And then this is a half silvered mirror. So out of all of these 50% of the photons, 50% of these will go through, so that's 25, and 50% of these will be reflected, so that's another 25. And likewise, out of these 50%, we will have 25% reflected and 25% transmitted. Okay, so in total, how much do we expect here? We expect 50% here, and we expect 50% here. That's what we expect just based on classical physics and classical probability theory. We expect that we have 50% of the photons here, 50% of the photons there. However, when we do this experiment, what happens is we actually end up with 100% of the photons over here. 100% of the time, we get a photon detected here, and we don't detect any photons at all here. So we end up actually with 100 here and 0 here. And this is counterintuitive. If you just know classical physics and classical probability, you would never guess that you would have 100% of the photons going here, because 50% of them came here. So the reason for this is actually quantum mechanics. And the photons are actually not particles where 50% go there and 50% go there. But really, the photons, they are like a wave, a quantum mechanical wave, not just particles, but they can also behave as waves. And these waves, they're really going everywhere. And you can have constructive interference and destructive interference, leading to 0 or 100%, depending on how the waves interact with each other. Okay, and Richard Feynman said of this, all we know is that it works, quantum mechanics. We don't understand why quantum mechanics works the way it does, but we understand that it works. We can mathematically predict that we will get 100% here and 0% here. So this is just telling you that quantum mechanics behaves a little bit differently from how we expect. And we can have actually, if we treat this path as a 0 in a classical computing sense, and this path as a 1, okay, just like in classical computers we have zeros and ones. When we have a wave going through both sides at the same time, we can consider this as a superposition of 0 and 1 at the same time in our quantum computer. Okay, so in classical computers we have ones and zeros, which are just distinct classical states. So in most CPUs, we have 0 as a low voltage, 1 as a high voltage, or in barcodes, we have thick lines and thin lines. We have thick lines and then a thin line and then a thick line. This is a barcode. Zeros and ones again. We can have optical discs like DVDs and CDs. 0 is just the absence of a microscopic pit on a reflective surface, and the 1 is the presence of a microscopic pit on a reflective surface. Okay, so there's plenty of different types of classical computers. Even in a disk, you can have north and south magnets being your zeros and ones, or magnets that are polarized in the north and south direction, facing certain ways. You can have zeros and ones that way. You can even have a DNA computer. Okay, this is a computer where if I have AT and CG, these pairs, AT is 1, CG is 0. The human body, it has 300 billion base pairs, 3 billion base pairs of ATCG. Okay, so there's 3 billion of these in the human cell. This DNA molecule is only taking up 0.2 micrometers of space. So you can have roughly 3 gigabytes of data in a DNA molecule, okay, if you store those as zeros and ones, but it's still a classical computer, okay? DNA computers are still classical computers. It's a different way of constructing a classical computer, but it's still a classical computer, or in this case, a classical storage device. Now let's get into quantum computers, okay? So in NMR, nuclear magnetic resonance, we have the spin of a particle, okay? If you learned maybe in your physics or chemistry class, an electron can have spin up or it can have spin down, okay? This is your 0 and 1. And if you've studied a lot of physics or chemistry, you might have learned that electron spins or nuclear spins, they come in triplet states or singlet states. So here, this is just 1, 1. This is just, don't worry too much about what's on the left because that's the notation for NMR. But here we have, if we look at this notation, 0 is spin up, 1 is spin down. We have 0, 0, and here we have 1, 1. Okay, this is 0, 0, and we have 1, 1. What is this over here? This is neither 0, 0 nor 1, 1. This is 0, 1 plus 1, 0 divided by the square root of 2. Okay, so this is not a classical bit. This is a qubit, or this is 2 qubits that are entangled with each other. Okay, so in quantum mechanics, we have various different ways that we can define our zeros and ones. In photonics, 0 is the horizontal photon that is polarized horizontally, and 1 is a photon that is polarized vertically. This is more similar to the first experiment I showed you, the Mach-Zehnder experiment. In atoms, you have ground states and excited states if the electron is in the ground state or if it's excited. In quantum dots, you can have an exciton at position 1 or at position 2. This is 0 or 1. And in all cases, we share the same property, that we don't have that the state is just 0 or just 1. It can be in a combination of 0 and 1, both at the same time, okay? So that is just some basics about qubits, quantum bits, basically. So let me go on to some simple quantum computing algorithms. Now let's say x is 0 or 1, and we want to know the function f of x, okay? So f of x will take the input 0 or 1, and it will give you some output, okay? Now we want to know f of 0 plus f of 1. And we don't know f of x because that's a black box. So we will have to learn what f of x is by applying f of x to the inputs f of 0 and f of 1. Now, someone, I don't know if the students are able to participate by answering in the chat or answering verbally, but I'd like to ask how many.
Hello, Dr. Nikkei.
Are the students able to answer this?
Yes, sure. You can answer verbally or typing in the chat.
Yeah. So we want to know f of 0 plus f of 1. So we have to evaluate f of x, and we need to know. So most people would guess that you would need to evaluate this twice. And on a classical computer, that's true. You have to evaluate f for the input 0. So you put 0 into this circuit, and you get f of 0, right? Okay, and then you store this information. Then you do 1, okay? You put 1 into here, and then you get f of 1 as the output, okay? So we have evaluated f of 0, we have stored it. We have evaluated f of 1, and we have stored it. Now we can add f of 0 plus f of 1, okay? So that's how a classical computer works. In a quantum computer, you only need to evaluate f of x once, okay? The reason why is because we put in a superposition, okay? We put in a superposition of 0 plus 1. This is 1 and 0 at the same time. Just like I told you in the Mach-Zehnder experiment, we had these photons going through, and after they hit the half-silvered mirror, they're now neither in path vertical or path horizontal. They're in both paths at the same time because they're acting like a wave instead of like a particle. Similar to that, we have here that if we put this qubit in this state into this function, we can actually evaluate f of 0 plus f of 1 with only one evaluation of f of x. Okay, this is called the Deutsche algorithm. Okay, how do I get back? Sorry about that. So this is called the Deutsche algorithm. And this was discovered by David Deutsch from Oxford University in 1985. Okay, and this was actually done in a real experiment in 1998. Okay, David Deutsch knew that the laws of quantum mechanics will allow us to compute f of 0 plus f of 1 with only one evaluation of f of x instead of two evaluations. He knew that in 1985, but this wasn't actually proven experimentally until 1998. And the person that did this, there was two people on this publication, Michele Mosca and Jonathan Jones, both of them from Oxford University. Okay. Now, let's say we have a more general version of this same problem. We have a function f, which is still a black box, but it's taking in not just one input, 0 or 1. It's taking in many different bits, okay? This can be 0 or 1. This can be 0 or 1. This can be 0 or 1. They can all be 0 or 1. So now, if I want to know if I want to know whether or not this function is constant or balanced, what I mean by that is a constant function. So a constant function is a function where no matter what the input, okay, if I put in 0, 0, 0, 0, 0, 0, 0, then I might get some answer. Maybe f of this equals 1, and maybe f of 0, 0, 1, 0, 0, 0, and I'll put a 1 here. This is just a different input. This also gives 1. And whatever my input, I get 1. Then this is a constant function, okay? Now, how many times do I have to evaluate this function in order to determine whether or not this function is constant? Okay? Now, I can't hear the audience, but I will just give you the answer. Usually, I would get the audience to answer so that I know you're really understanding this. But I'll tell you the answer. You would have to test this function 2 to the n times. Okay? The reason why is because if I evaluate this for the input 0, 0, 0, 0, and I get 1, then I don't know if the function is constant or not, because I haven't seen what happens to other inputs. Now I do it with a different input, 0, 0, 1, 0, 0, 0, 0, 1, and I get 1 again. So I think maybe it might be a constant function because 2 inputs gave me 1. But the next input might give me 0. Then it's not a constant function. So I have to evaluate this function for every single possible input, which is 2 to the n different possible inputs. Okay, that's how many times I have to evaluate this function on a classical computer to determine whether this function is is constant or not constant. Okay. On a quantum computer, you can guess how many times we have to evaluate this function. Maybe you think it's 2, maybe you think it's n, maybe you think it's 2n. Okay, I will give you the answer. On a quantum computer, we can evaluate whether or not this function is constant or not constant with just one application of the function. We do not have to try 2 to the n different possibilities. Okay, what we're going to do is we're going to put a qubit here. Okay, so this is my 0 plus 1. Okay, and we'll put another qubit here, also in a superposition of 0 or 1. Okay, and then we'll put a qubit here, we'll put a qubit here, we'll put a qubit here, we'll put a qubit here. And in the end, what we have is all possibilities. We'll have basically 0, 0, 0, 0, 0 from the fact that this is both, every qubit has a 0 in it. Every qubit has a 1 in it. So we also have the 1, 1, 1, 1 state. We have that one in here too. Okay, and then we also have the 0, 1, 0, 0, 0, 0 state. So we have that one. We have all possibilities, all 2 to the n possibilities we have if we insert these qubits into the function. So we only need to evaluate this function once in order to know if this function is constant or not. This is called the Deutsche algorithm. Okay, it was first published by Deutsch and Joza in 1992, and Michele Mosca and Richard Cleve and some others, Arthur Eckert and Machiavella. There's several authors that improved this Deutsche algorithm, and the final version, which you see in textbooks, was done in 1996. Then this was done in a real experiment in 2002. So this isn't just theoretically possible. This has actually been done in an experiment where there's a black box function, and it was determined whether it was constant or not constant with just one application of the function. Okay, So now let's get into some more useful algorithms. If I ask the audience, what do you know about quantum computing? What algorithms do you know that quantum computers can do? Most people will say that they know that quantum computers can factor numbers more efficiently than classical computers. And so here we have a number of experimental realizations of Shor's algorithm from 1994, which is an algorithm for factoring numbers with a polynomially scaling number of quantum gates. On a classical computer, there is no known algorithm that can do this with a polynomially scaling number of gates. Okay, the number 15 was factored in many different years with fewer and fewer qubits. And the number 21 was actually factored with 2 qubits and 1 qubit. This was in 2012. Now, the number 56153 was factored with only 4 qubits much later, and it didn't use Shor's algorithm. Okay, now if I wanted to teach you Shor's algorithm, I'm going to have to teach a whole course on quantum computing. I'll have to teach you the Hadamard gate, the controlled knot gate, the quantum Fourier transform, and a lot of other things. I teach a 1-week course on quantum computing where I teach every day for 8 hours, and at the end of the week, I teach Shor's algorithm. So this is actually this algorithm from 1994 for factoring numbers. It's a good algorithm, but it will take a long time to teach that algorithm. Okay, but there's newer algorithms for how to factor numbers on quantum computers. One of them uses discrete optimization, and this I can actually teach you right now. I don't have to teach you a 1-week course to teach you how this algorithm works. Okay, so we have the number 143. In binary, that's 10001111. Okay, now P times Q equals 143. We want to know P and Q that multiply together to give 143. But right now, P and Q, they're both unknowns. So we have these variables, P1, P2, Q1, Q2. Those are variables, they're unknowns, and we want to determine what they are. Okay, am I going too fast?
No, I think it's fine.
Okay, so the last bit is a 1, because if the last bit was a 0, then we have an even number. You know how to factor even numbers? You divide by 2. You just divide by 2. So factoring numbers is only hard if the factors are odd. So I'll make the last bit 1 so that these are odd numbers. And the first bit has to be 1, because if it's not, then it's not the first bit. Okay, we never have something starting with 0. So we have 4 variables here, P1, P2, Q1, Q2. They're all either 0 or 1. Okay, and now we're going to multiply P times Q the same way we did in school when we were 10 years old. We multiplied 2 numbers and we make a table and we add up these columns. Okay, when we add up these columns, what we get is a system of equations. Okay, and here we have sometimes, if, for example, when we're multiplying 2 decimal numbers, we have 5 times 6, that's 30. 30 is too big to put in one digit, so we have a carry variable, so that's why we have this Z12. Okay, so now let me ask a question. If A is 0 or 1, B is 0 or 1, and C is 0 or 1, all of these variables, they're either 0 or 1, then what is the value of C? Okay, can anyone answer this?
Students?
C can either be 0 or 1, and A and B can either be 0 or 1. What happens if C is equal to 1? Well, maybe some of them might not be unmuted. So I'll just give the answer. If C is equal to 1, we will have a 3 on the right side. And if A and B are 0 and 1, we cannot possibly have 3 on the left side. So C has to be 0. Okay, that's the first thing I'm going to tell you. So now we know that if I have P1 plus Q1 equals 1 plus 2 Z12, Z12 equals 0, because it's impossible for it to be 1. So this is also 0. Likewise, Z24 is 0, because I have 1. If Z24 is 1, then we have 1 plus 4, that's 5. But we don't even have 5 things on the left side, so there's no way, even if these were all 1s, you have 1 plus 1 plus 1 plus 1, you have 4 here, you can't have 5. So many of these things become 0, and then we end up with this very simple set of equations, okay? If I solve this set of equations, if I find the binary P1, P2, Q1, Q2, these are all either 0 or 1. If I find those zeros and ones that satisfy this set of equations, then I have found the P and Q such that P times Q equals 143. Okay, now a new question. What is the minimum value of this function here? What's the lowest that it can possibly be? P1 and Q1 are binary variables again. Because this is squared, we cannot have a negative number. It's impossible for this to be negative, okay? So the minimum, I'll say minimum on this side, the minimum of this function equals 0, okay? Now, if I minimize this function, I'm finding the P1 and Q1 such that P1 plus Q1 minus 1 squared equals 0, okay? If I minimize this function and I find the P1 and Q1 such that this thing is 0, then I'm finding the P1 and Q1 such that this equation is 0. Now, if I square root both sides, I get P1 plus Q1 minus 1 equals 0. Okay? So minimizing this function here, that is the same as solving this equation here. P1 plus Q1 minus 1 equals 0. Okay? P1 plus Q1 minus 1 equals 0. Okay? That's the same as this equation here. Okay? So if I minimize this function, I'm finding the P1 and Q1 such that this function is 0. That's the same as solving this equation here. Okay? Now, similarly, what's the minimum of this big function here? The minimum of this function, well, this function, it cannot go below 0, okay? Because we have the sum of 3 squares. If we want the sum to be less than 0, one of these has to be negative, but they're all squares. So the minimum of this is 0. And to get the minimum of this being 0, to get the minimum of this function, we need this to be as small as possible. We need this to be as small as possible. And we need this to be as small as possible. So we have to minimize this function, and this function. And if I find the P1 and Q1 that minimize this function, I'm solving this equation. And if I find the P2 and Q2 that minimize this function, then I'm satisfying this equation. And if I find the P1, P2, Q1, Q2 that minimize this function, then I'm also satisfying this equation. So I'm satisfying this entire system of equations by minimizing this function, okay? I'm minimizing this function. It's the same as solving the system of equations. And solving the system of equations means that we know P1, Q1, P2, and Q2. So we have now factored the number 143 by finding the variables associated with the factors. Now, instead of doing this on a classical computer, we can't minimize this function very easily. Typically, if I have a function and I want to find the minimum, I set the derivative to 0, okay? The derivative to 0. However, for this to work, the function must be differentiable and continuous, okay? You need a continuous function. But here, I'm dealing with discrete variables. P1, Q1, P2, Q2, they are all just discrete binary variables. So what I have is a function that looks like this, okay? Now, this might be 0, 0, 0, 0, this is 0, 0, 0, 1, this is 0, 0, 1, 0, but there's nothing in between, okay? There's nothing in between. We don't have a derivative. If you find the minimum, if you test the function for various different inputs and you find that this is the minimum, how do you know that is the real minimum until you have tried all of these other ones, okay? So you have to try all 2 to the n possible. If I have n variables, p1, q1, p2, q2, q3, p3, q5, if I have n variables, there's 2 to the power of n different, on a classical computer, I would have to test this function for 2 to the power of n different inputs, okay, and find which one gives me the lowest value in the function, okay? So that's hard to do on a classical computer. If I have 1,000 variables, then I have to test 2 to the power of 1,000 inputs, okay? But in a quantum computer, the solution is given by finding the ground state of 4 qubits that are coupled together with this Hamiltonian, okay? If you don't know what a Hamiltonian is, that is okay. Each P1, Q1, P2, Q2, these are just qubits, okay, like spin one, spin up, spin down of a particle. So I'm going to have many different particles with spin, and I'm going to couple them with different coupling strengths, okay? I'm going to couple qubit P1 and qubit Q1 with a strength twice as big as the strength that I couple qubit P1 with qubit Q2, because when I expand this function, I end up with some coefficients, okay? And I'm going to couple qubit P1 to qubit Q1 with a strength twice as big as this strength. And I'm going to couple all of my 1,000 qubits, for example, with strengths proportional to the coefficients in the Hamiltonian. And then I'm just going to cool this system of 1,000 spins down to absolute zero temperature almost, so that I see what configuration these spins are in when they are in the ground state. That's the lowest energy state. And that ground state is going to depend on these coupling constants. So for every function, I will have a different ground state, but that ground state can be determined by finding the state or the configuration of spin up, spin down, such that this system of 200 electrons or 200 protons or 200 spin half particles, the configuration in which the 200 spins are in their ground state, okay, the lowest possible energy state. And it's easy to get 2,000 qubits. That's just 2,000 spin half particles. Okay, that can be 2,000 electrons or 2,000 protons in NMR, for example. Okay, so factoring 143, in our Hamiltonian, we use the sigma z operator. This is 1 and -1. If P1, Q1, P2, and Q2 are all described by this matrix, then the overall Hamiltonian of 4 qubits, that's a 16 by 16 matrix. And we find that the states, or the eigenvectors with the smallest eigenvalues are 0. And we find that with 2 different eigenvectors, one corresponds to p equals 11, q equals 13. The other corresponds to p equals 13, q equals 11. So we have factored the number 143 because we found these eigenvectors corresponding to p equals 11, q equals 13, and p equals 13, q equals 11. Those eigenvectors are encoding these p1, q1, p2, q2 that minimize or find the ground state of this Hamiltonian. And by minimizing this Hamiltonian or finding the ground state of this Hamiltonian, we are essentially finding the P1, Q1, P2, Q2 that satisfy our initial equations, which correspond to the table. So 143 that equals P times Q, where P1, P2, Q1, Q2 are determined by finding the ground state of the Hamiltonian. Okay, so we wrote a program where you give the program a number, and it tells you the Hamiltonian that factorizes that number. So we can factor larger numbers, and we actually went all the way up to this number over here in 2014, and we found that the Hamiltonian that factorizes this number can be represented with just 4 qubits. So with 4 qubits, we could factor a fairly large number. This, at the time, was regarded as the new largest number factored on a quantum device. Okay, so this came in the news all over the place, and we actually, so in 2012, the experiment was done. 2014, we discovered that we could do this with 4 qubits. Later, we proposed 291311 could be factored with 6 qubits. Okay, and so in the integer factorization records, we were recognized in November 2014 as having factored the largest number on a quantum computer so far. Okay, and the reason this is important is because factoring numbers, the fact that factoring numbers on a classical computer is difficult is the basis for the RSA crypto system. Okay, so if you're interested in cryptography, you probably know that it's hard to break codes that are ciphered using the RSA crypto system if you can't factor a big number. And so this is an algorithm that was written by Rivest, Shamir, and Edelman in 1977. Okay. And that algorithm is still being used today by many people to secure their information, to secure financial information, for example. And after the paper that I published on factoring 56153,
people to perform operation on data in very different way than traditional computer. Speedups are extraordinary, something called.
Sorry about that.
Yeah, no problem. So after this publication of factorizing 56153 with 4 qubits, that paper was actually mentioned in this article called NSA Plans for a Post-Quantum World. Okay, and one of the biggest honors for me was when Ronald Rivest, he is the R in RSA. Okay, the R in RSA, he mentioned my work in one of his talks, okay, when he was talking about factoring big numbers. Okay, so the new record that we published in 2017 was that we factored 291311 on a quantum computer. And you're probably wondering now, how do I find the ground state of a Hamiltonian with 100 qubits? Okay, I showed you how to do it with 4 qubits. It doesn't look that hard. But for 128 qubits, there was in 2011, the first commercial quantum computer was released. That's this DWave machine over here. This was sold for $10 million US, or many millions of Indonesian rupiah, okay, to the company Lockheed Martin. And then the DWave II was published the next year with 512 qubits. That was sold to NASA and Google for their Quantum Artificial Intelligence Lab. The DWave II, which had only 512 qubits, you can see this paper published in 2014 in the journal Science. Okay, they did lots of different experiments with the DWave II and with a classical algorithm called simulated annealing. Now, this is the amount of time that it took to do it on a classical computer with simulated annealing, and this is the amount of time that it took on the DWave. Okay, and you can see if the data point is in this corner, then it means that simulated annealing on a classical computer was faster. If the point over here, if the point is over here, then that means that DWave II was faster. Now you can see that there's a lot of instances of problems for which the DWave machine was finding the ground state of a 512 qubit Hamiltonian faster than the classical computer, using what these authors in 2014 thought was a state-of-the-art algorithm for finding the ground state of a 512 qubit or 512-bit optimization problem. Okay, so already in 2014, you can see the D-Wave is outperforming in terms of the amount of time that it takes to find the ground state of these optimization problems. Okay, so that's in 2014. Then 2015, 1,152 qubits. This is a bigger quantum computer sold to Los Alamos National Lab. That's the same place where Richard Feynman and Enrico Fermi and a lot of other people worked during World War II. Then DWave IV in 2017, this has 2,000 qubits, okay? And it's being used by Volkswagen, Temporal Defense Systems, Virginia Tech, Denso Corporation, Oak Ridge National Laboratory, University of Southern California. Lots of different customers now using the DWave IV machine. Now, the most recent machine, the DWave V, it says 5,640 qubits. There's something fundamentally different between this quantum computer and all of these, okay? These ones have the qubits connected together by a certain graph called the Chimera Graph. And what they did in these computers, in these bigger and bigger computers, they just made more and more qubits connected by the same graph called the Chimera Graph. This DWave V actually uses a new architecture where the qubits are coupled according to something called the Pegasus graph, okay? Now the Pegasus graph, when it was first announced at the AQC conference in 2018, they showed the Pegasus graph, they showed it on a slide, but they didn't explain what the connectivity between the qubits are in the Pegasus graph. So this was actually reverse engineered by myself and two colleagues, Szilard Szalai and Nicholas Chancellor. And we were actually the first to reverse engineer and determine how the qubits are coupled in the DWave V. And then we made it open source in this paper, which is on arXiv. So this is free to download. Okay, so this actually, I'd given a talk at DWave a couple years ago actually it wasn't, yeah, it was 2 years ago in 2019. Right before I gave the talk, I Googled Pegasus and I saw that they had announced it 18 hours before I gave the talk. Okay, so I'll explain to you a little bit what I mean by the Chimera Graph and Pegasus Graph. Now this is the Chimera Graph over here. And this is the optimization problem. This is the function that we want to optimize to factor 143, for example. And you see let's call P1 is qubit 1. P2 is going to be qubit 2. Q1 will be considered qubit 3. And Q2 will be considered qubit 4. Okay? Now, if this is qubit 1, qubit 2, qubit 3, qubit 4, okay, these are all qubits in the DWave hardware. These qubits are connected by a certain graph. So 1 is connected to 2, okay? But 1 is not connected to 3, okay? And 3 is not connected to 5. And 1 is not connected to, qubit 1 is not connected to qubit 32, okay? If the qubits are too far away from each other, we cannot couple them together. And so if our function has, for example, we want to minimize a function where qubit 1 is coupled to qubit 32, that would be impossible on the Chimera graph. This is the Chimera graph, okay? It would be impossible to do that ordinarily to qubit to solve an optimization problem where variable represented by qubit 1 is coupled to the variable represented by qubit 32. Okay, so that's the importance of the Pegasus graph, which is on the right side. Okay, so the first 4 generations of D-Wave machines, they just made more and more of these unit cells. Okay, instead of 2 by 2, they had, okay, this is the Chimera graph. Okay, these are all just different ways of representing the Chimera graph. Here we have 4 qubits coupled to 4 qubits. Here it's 4 qubits coupled to 4 qubits. These are just 3 different ways of representing the same graph. This is Chimera here. So what they did was, you can imagine DWave 1 maybe has only a few of these qubits coupled to each other in the Chimera graph, and the DWave 4 has 1,152 qubits coupled to each other in the same graph. Okay, the difference now is in Pegasus, you have a much more complicated graph. This over here is still, I'll explain it here. Here we still have a Chimera graph. Okay, this is exactly, we see this 4 by 4, 4 by 4, 4 by 4. All of these are still there in this arrangement of qubits. But then we have basically 3 layers of Chimera graphs. Okay, maybe easier to see over here. We have 3 layers. Imagine in 3 dimensions you have 3 sheets of paper that are on top of each other, and each of these sheets of paper is a Chimera graph. Okay, now each of these sheets of paper are connected. The qubits of this Chimera graph are coupled to the qubits of the next Chimera graph. Okay, so that is Pegasus. The 5th D-Wave machine is connected with this graph rather than just this graph. Okay, that means that the qubits, now maybe qubit 1 can be coupled to qubit 32. So we're a lot more flexible. Okay, now I did this paper again with Nick Chancellor. This is embedding certain types of graphs onto Chimera and Pegasus graphs. These are various different graphs where if I have 4 qubits that are connected in this way, P1 is connected to P2, P2 is connected to P3, P2 is connected to P4, but P3 is not connected to P4. That's this graph over here. Okay, I can also have this graph over here. It looks like a coat hanger, like I'm hanging my clothes on something. So one thing to point out is that in these Chimera graphs, where we have unit cells where there's 4 qubits coupled in this certain way, this Chimera graph, for the propeller, for this graph, we can just embed it onto the hardware very easily. We have this red qubit is coupled to 3 black qubits. It's the same thing here. Okay. For the coat hanger graph, you have a triangle, and you might know that this K44 graph. That's, if you know graph theory, you call this graph K44 because we have 4 qubits here, 4 qubits here. These are connected to these are connected to these, but these are not connected to each other. So we don't actually have any triangles. There's no cycles of length 3. There's no triangles there's no triangles in this Chimera graph. Okay, but the problem that we want to optimize does have qubits connected in that way. So now what we're going to do is we're going to represent 2 physical qubits by 1 logical qubit. Now this logical qubit, which is represented by 2 physical qubits, it's connected to this. So if this is qubit 1, this is qubit 2, and this is qubit 3. Qubit 1 is connected to qubit 2, qubit 3 is connected to qubit 2, and qubit 3 is connected to qubit 1. So we have our triangle. But it came at the expense of an extra qubit. So if you want to optimize a function on a D-Wave machine, and you think that this binary optimization problem only involves 2,000 variables, and therefore you can solve it on the D-Wave machine that has 2,000 qubits, it might not be possible, because if your function that you want to minimize has a certain connectivity which is not naturally embedded onto the DWave hardware, then you will need to use auxiliary qubits. So some of the 2000 qubits will be wasted on this embedding. Now here's many different graphs, and you can see this graph K6. K6 has 6 qubits, all of them connected to each other. You can see we have a lot of physical qubits representing one logical qubit, okay? 3 physical qubits have to represent this one logical qubit. And then here, 2 qubits are representing one logical qubit. So it gets bad very quickly, okay? Now, there's another thing I want to say. So you understand if I have qubits 1 and 2, qubits 2 and 3, qubits 1 and 3, these are coupled with each other. They have to be, the graph connectivity between these qubits, okay, maybe the graph looks like this or like that, who knows. There's maybe 20 qubits coupled with this graph. You have to embed that graph onto the hardware. That's called compiling. That's one of the steps in compiling the problem to work on the hardware, because the hardware doesn't know how to do anything else. Now, there's another interesting thing here. Here we have 3 qubits in one term, okay? These are simple graphs, the Chimera and Pegasus architecture. These are simple graphs. Every qubit is coupled to another qubit, but it can't. You don't have 3 qubits coupled together like in a hypergraph. There's no such thing. The interactions physically between the qubits, imagine you have like Q1, Q2 over R squared, where R is the distance between the qubits. That's a 2-body interaction. You just can't have this 3-body interaction on the DWave machine naturally. So now we're going to treat that. I'm going to show you how to compile the 3-body interactions onto the DWave hardware. So here's a function, B1, B2, B3. B1, B2, and B3, they can all either be 0 or 1. The minimum of this function is -1. That happens if B1, B2, and B3 are all 1, okay? If Bi for all I, these are equal to 1, then I have 1 times 1 times 1 times -1. This is -1, all right? If any of these B's are a 0, then I get 0 for this function, okay? So now let's look, this is a cubic function. There's 3 variables in one term. This over here is quadratic because each term has only 2 operators, okay? Now, let's see what happens here in this function. If B1, B2, and B3 are all 1s, okay, then this is -1, this is -1, so I have -2 plus 1, okay? So that is -1, okay? So I have -1 if B1, B2, and B3 are all equal to 1, then I have -1 over here. That's the same as what I had for the cubic, okay? So B1, B2, B3 all 1, that gives me -1. If B1, B2, B3 are all 1, then on the left side for the cubic, I have -1, and for the quadratic, I also have -1. Now, what happens if I make B2 equal to 0? Okay, if I make B2 equal to 0, this on the left, this should be 0, because one of these is 0, then the product is 0. But here, what I will get is, I will get, this is 0, and this will be B1 times B3, this will be -1, and this will be +1, so I will get 0 again, okay? So if I make B2 equal to 0, then I get the same on the left side as the right side. What happens if I make B2 equal to 0 and B3 equal to 0? Again, the left side is 0, but here I have 0 and 0, and then I have +1, because I have 0 here and 0 here, but B1 is still 1, so I have positive. Now the left side and the right side do not equal each other, okay? If I'm just looking at this part of the function. So quadratization, you think you might be able to turn this cubic into an equivalent quadratic by just doing this, but that's not enough, okay? Because it doesn't work all the time. Now let's look what happens here. We have B1 still equals 1, so we have -1 here. B2 and B3 are 0, okay? That's we already set that to 0 over here. So now we have over here negative BA, where BA is an auxiliary variable. So we have 4 qubits instead of 3. And now if I minimize this function, okay, you know, the problem is I had +1 over here. You can forget about this now because that was for the case where I had all 3 of them equal to 1. So here I have, if B2 is 0, this is 0. B3 is 0, this is 0. B1 is 1, I have +1. Now my function is -BA plus 1, okay? What's the minimum of this? The minimum of this will happen when BA is equal to 1. So this will be -1 plus 1. That's equal to 0, which is what we had on the left side. So by introducing this auxiliary qubit, we can make a quadratic function that is mathematically equivalent to a cubic function. Okay? The cubic function and the quadratic function are the same when we minimize over auxiliary variables. Now, so unfortunately, whenever we have a cubic term, that means we need auxiliary qubits. Okay? So this is cubic and this is quadratic. Okay? So if I want to factor a big number, RSA 232, this is a number that is really of interest in cryptography because it's 232 digits long. It's very hard to factor that on a classical computer. This would need 5,893 qubits if we have a quantum computer where we can have 4 body interactions, P1, P2, Q1, Q2, all coupled at the same time. Now, if we can't have 4 body interactions, we need auxiliary qubits to turn these 4 body interactions into 2 body interactions. Okay, but remember, the Chimera graph or the Pegasus graph, they don't allow just any 2 body interactions where B1 interacts with B32 and B1 interacts with B146. Okay, you can only have the qubits interacting according to a certain graph. And remember, to embed an arbitrary graph onto a DWave hardware, for example, you will need to have maybe 2 physical qubits representing 1 logical qubit. And because the number of possible, if I have 5,000 or 6,000 variables, then the number of possible 2-body interactions is 6,000 squared, okay? Then, you know, that's, you can easily get to 1 billion qubits needed. So even though the DWave machine has 5,000 qubits right now, the problem is that those qubits cannot be interacting in 4-body interactions, and they don't have arbitrary couplings between the qubits, and therefore you need a DWave machine with 5.5 billion qubits to factor this number that's 232 digits long. Now, in 2015, with some undergraduate students of mine, Emil Okada and Richard Tanburn, Emil is now doing his PhD at Oxford University in the mathematics department. Richard Tanburn finished his undergraduate. He is now working at Google's DeepMind. DeepMind is the artificial intelligence company that wrote the AlphaGo. AlphaGo. This is a software that beat the world's best human Go player. Go is like a board game that's played in China and Japan. And the best player in the world was beaten by this computer program, artificial intelligence. Okay, Richard Tanburn is working there now. So we came up with this method called deduction reduction. We come up with a deduction about the constraints on our optimization problem, and we use that to reduce multi-qubit interactions, okay, reducing multi-qubit interactions in adiabatic quantum computation. We do it without auxiliary qubits in this paper, okay? And likewise in this paper, using the split reduct method, we did it without auxiliary qubits. So we came up with a couple of different methods for quadratizing high degree optimization functions without auxiliary qubits. And we applied this to determining Ramsey numbers. I don't know how much you know about graph theory, but Ramsey numbers are a very interesting topic in graph theory. Okay, so they were experimentally determined in a experiment by DWave themselves, okay, published in one of the most prestigious physics journals in the world. This is Physical Review Letters in 2013. They found the Ramsey number R82 using 84 qubits, where only 28 of the qubits were computational qubits. So 28 qubits were logical qubits, and about 50 qubits were auxiliary qubits, because the problem had cubic terms or degree 4 terms, and the graph connectivity wasn't exactly the same as the Chimera graph. So 50 qubits were wasted. If I have 2,000 qubits, then it's very disappointing if I can only use 100 of them, if I can only solve a 100 qubit optimization problem. However, sometimes you have to use most of the hardware qubits as auxiliary qubits, and then you can only solve a problem with only 28 qubits. Okay. Now, with the split reduct method, we applied it to the determination of Ramsey numbers. Okay, with the same quantum computer as DWave used, we were able to do R16.2 and R4.3, which are much bigger Ramsey numbers than R8.2. Okay, twice the number of nodes in this graph. Okay, so Ramsey numbers are very interesting. There's only been 1, 2, 3, 4, 5, 6, 7, 8, 9 of them discovered in all of history. Okay, in the entire history of humanity, only 9 Ramsey numbers have been determined. Okay, and the most recent one was in 1995. Okay, so if we could, for example, find Ramsey 310 or Ramsey 4.6, then the quantum computer has found the answer to a calculation that a classical computer was never able to do. This is the number of qubits and the number of different interactions you need to do Ramsey 10.3 and to do Ramsey 4.6, which I showed you just now. Okay, now you only need 780 qubits to find R10.3. So this has never been found on a classical computer now. We know that it's at least 40 and it's at most 43, but we don't know the value of this Ramsey number. So we can find the Ramsey number with only 780 qubits. We just turned the Ramsey number problem into an optimization problem with 780 binary variables. The problem is that you have 30,000 quadratic terms and 10,000 cubic terms, okay? Unfortunately, these cubic terms, they will need auxiliary qubits to quadratize, usually. But we came up with methods to quadratize functions without auxiliary qubits. And when we applied this deduction-reduction method, here you can see some of these Ramsey numbers, like to find Ramsey 4.6. You have 15 qubit interactions, 15 binary variables in one term, and you have 6 billion 10 qubit interactions. Okay, now here to find Ramsey number 334, you have 20 million 7 qubit interactions and 30,000 12 qubit interactions. Okay, but with deduction reduction, with 0 auxiliary qubits, so it's still 870 qubits, we no longer have these interactions. Okay, all of these multi-qubit interactions are gone with the same number of qubits as what we had before. Okay, so that's the power of this deduction reduction method, which my undergraduate student Richard Tanburn came up with while he was an undergraduate student. Now, we can do further reduction. We can do this RSSR method, FGBZ, clique substitution, direct substitution, generalized roof duality. And by doing all of that, we end up with this cute little table over here, where we find that we can find an unknown Ramsey number. R333 is actually known to be 17. But if we wanted to do this on a quantum computer, we could do this with 408 qubits and 2040 cubic interactions, which these cubic interactions would then have to be quadratized with auxiliary variables. But we were able to get most of the problem solved without auxiliary variables. Okay. One thing that I didn't show is that even though it looks like I've made the number of multi-qubit interactions very small here, there's also 800 million 45 qubit interactions. Okay, 800 million 45 qubit interactions. So even though it looks like it's easy, we still have to come up with a way to quadratize these. That will need auxiliary qubits. So we can apply all these methods as much as we want, but we still need to quadratize these high degree functions. So here we have degree k function. I showed you if I have a cubic function, I can always quadratize it with just one auxiliary variable. Now, similarly, I can take a k degree function and turn it into a k minus 1 degree function with one auxiliary variable. Then I can make it k minus 2 with another auxiliary. Then k minus 3 with another auxiliary. So if I have a degree 5 function with one auxiliary qubit, I make it degree 4. And then another auxiliary, I make it cubic. And then another auxiliary, I make it quadratic. Okay? And in the end, we need k minus 2 auxiliary variables because, well, how many variables did we need here? We needed 3 auxiliary variables to do a function of degree 5. So 5 minus 3 is 2. We need k minus 2 auxiliary variables for each term that is degree k. But later on, it was discovered you could do this with k minus 1 over 2. So this is, from computer science terminology, this is k over 2. And this is just order k. Okay, so this is half the number of auxiliary variables when we get to this method over here. And then we can actually do this with k over 4 auxiliary variables. This was discovered in 2018. Okay, this was discovered in 1975. And this was discovered, I think, in 2011. And this was discovered in 2018. K over 4. However, you can also do it with log of k auxiliary qubits. This was discovered even later. And log of k minus 1 auxiliary qubits. Just when you thought that it got perfect and it can't be any better, you can actually do it with log of k minus 1 auxiliary qubits for each positive monomial of degree k. Okay, now all of these methods are explained in my book. This is an open source book online. You can download this for free. It's called Quadratization in Discrete Optimization and Quantum Mechanics. So if you want to optimize a degree k function and you can't do it because it's too hard to optimize a degree k function, you can quadratize it into a degree 2 function. You can see here every term has only 2 variables at the most. Okay, and here likewise you multiply this by this, this by this. They're all quadratic. Okay, so there's 75 different methods to quadratize functions, all described in this book. This book is an open source book, so you can always add functions, you can remove functions, whatever. If you find a new quadratization, you can always add that to that book. We have about 65 members in HPQC Labs, the High Performance and Quantum Computing Laboratory. We have about 65 members on GitHub. And we have a book that's open source on how to quadratize things. Then we have some code. So if we have a function that is degree k, we can turn it into a quadratic function using this code. Okay. Now, I talked about DWave for a while. DWave is not the only company making quantum computers. Okay, so Google's hardware lab has a 9-qubit quantum computer. This is back in 2016. They now have a bigger quantum computer. I'll talk about that later. But IBM, May 2016, they had 5 qubits. May 2017, they had 16 qubits. Okay, now Intel, on October 10th, 2017, that's just a few months after IBM released the quantum computer with 16 qubits, Intel releases a quantum computer with 17 qubits. Okay, just a few months later. Now this is October 10th, 2017. November 10th, 2017, 1 month later, IBM says, oh, we actually had something bigger than 16 qubits. We just didn't tell you. But because Intel told you about the 17-qubit computer that they have, we're going to tell you about the 50-qubit computer that we have. Okay, so this is what the quantum computers look like. This is DWave, IBM, Google, IBM, DWave, Intel. This is what they look like. And on DWave, if you have 900 qubits, for example, this is how long it takes in microseconds. So 10 to the power of 4 times 10 to the minus 6. So 10 to the minus 2 seconds it takes to find the ground state of this, or to find the best they possibly could, the closest that they could possibly get to the ground state for about 900 qubits. With 0.01 seconds, they found the ground state. Now, the state-of-the-art algorithm in this paper that they published, well, at least the authors thought that this was the state-of-the-art classical algorithm for finding the ground state of a 900-qubit Hamiltonian. It took, 10 to the power of 11, that's 10 million microseconds, okay? This took 7 orders of magnitude. There's a difference of 10 to the power of 7 between this and this. So 10 million times slower. This is 10 million times slower than the D-Wave. And Hartmut Neven, the director of engineering at Google's hardware lab, he said at a conference at the APS meeting, American Physical Society meeting, he said that $1 million went into this calculation, okay? And it was still 10 million times slower than the D-Wave machine, okay? Now this, I told you that D-Wave's, the DWave II was sold to NASA. This is nasa.gov government. NASA has on their website, the DWave II, they explain that it uses only 12 kilowatts of power. Compared to the average supercomputer in the United States, the average supercomputer uses 4,100 kilowatts, the average of the top 10 supercomputers. So forget about speed. Yes, the D-Wave was 10 million times faster than the state-of-the-art classical algorithm in that paper I showed you just now. However, it's also 1,000 times, almost 1,000 times, there's maybe 300 times, 400 times, 400 times more energy efficient, okay? The next thing I'll show, this is the Green 500 list. This is the 500 supercomputers in the world that are the most green. That means the most environmentally friendly. Now, the first one has only 700,000 cores on the computer. 700,000 cores isn't really enough. If you want to do this calculation, if you want to use the same algorithm, if you have 700,000 cores, then this calculation might be 700,000 times faster. But the D-Wave is 10 million times faster, right? It's 10 million times faster. So 700,000 times faster is not good enough, okay? Now, there is a computer in this Green 500 list, the Gyoko, a Japanese supercomputer with 20 million cores, 20 million CPUs. So this can definitely, you can use 10 million cores, and then the classical computer is getting the ground state of the Hamiltonian equally fast compared to the D-Wave machine, okay? Because it has 20 million, it has enough cores to do 10 million calculations at the same time. However, it's using 1,350 kilowatts of power. 1,350 kilowatts of power. That is more That's 100 times more than the DWave machine. So the energy efficiency is something people don't talk about, because everyone thinks quantum computers are just faster than classical computers. But quantum computers might be energy efficient. This over here is the Summit supercomputer. Right now, this is the world's fastest supercomputer, or at least the biggest supercomputer in the world. It's in the United States at Oak Ridge National Lab. Okay, there's so much. This is the size of a football field, just in supercomputers. The number of wires you have here, it's probably enough to get you from here to Mars if you stretch those wires out. Okay, and the DWave machine, it's just this. Okay, this is the DWave machine. In this box, all it is a refrigerator to cool down the qubits to their ground state. Okay, now why is Google buying this? This is for the quantum artificial intelligence lab. So we could do quantum artificial intelligence, quantum neural networks, for example, if you're into neural networks. Myself and some colleagues, so DWave supercomputers, they use small quantum interference devices. Superconducting quantum interference devices. So they use superconducting qubits. They operate at 80 millikelvin. We don't yet have high temperature superconductors that can work at normal conditions. So we have to go down to very low temperatures for these superconductors to work. With some colleagues at the Space Research Institute, we managed to, this is a paper I did in 2015 in Applied Physics Letters. It was actually chosen as the editor's pick and the journal cover of Applied Physics Letters that year. We explored doing quantum computing with quantum dots instead of superconducting qubits. And we found that we can get the coherence times long enough at liquid nitrogen temperatures instead of liquid helium. So 77 Kelvin instead of 80 millikelvin. Now for real world applications, computer vision, this is the first image of the black hole. I can tell you that this is not an image with an ordinary camera. This is actually computationally, there was a lot of calculations that were done to reconstruct this image. If we have, for example, this image where someone took a photograph and then they folded it in half and then they damaged the photograph, we can actually use artificial intelligence to get what the photograph would have looked like. Although you can still see some damage here, you can see a line, but it's not as bad as before because of artificial intelligence. We take billions of damaged pictures and billions of not damaged pictures, and the artificial intelligence learns. In this case, we had an image that was damaged by this. The artificial intelligence gives us this. Perfectly, it's called infilling. It's called infilling of an image. Infilling. And this is a big topic in artificial intelligence, okay? This is unblurring, okay? We have a blurry image and we find the sharp version. So if you take a picture on your phone and your hand is shaking, then you take this image. However, the computer software can actually get the sharp version because it compares billions of blurry images to billions of sharp images, and it learns what is the difference between them, and then it predicts what the sharp image would have looked like. So this is the Hamiltonian for computer vision now. We have all the pixels in the image. These are the binary variables, zeros and ones for each pixel to tell you if there's a pixel there or not there. These are the new pixels, and the minimum of this function is 0. The minimum of this function is 0, which happens when the new pixel equals the old pixel. Okay, so this is there to maintain fidelity to the original image, because you don't want a blurry cat when it goes through the image processing algorithm. You don't want that to become a sharp dog. You still want it to be a cat. So you want the new pixels to be similar to the old pixels, but instead of optimizing just this function, which would be nv equals xv at the optimum, we want to optimize that function with this function at the same time. And this alpha and the j, those are calibrated by looking at a billion blurry images and a billion sharp images and comparing them. Then we optimize the alpha and the j, these parameters, such that minimizing this Hamiltonian will unblur the image, but we don't want to unblur it too much. We still want the image to look similar to the old image. So we're going to minimize these two functions at the same time. And that's the minimization problem for computer vision. And this can be done. There's an Android app for this. It's fairly decent, but we need something faster if we're looking at solar system data from big telescopes. These are images that are several terabytes in size. Then we can't do this classical algorithm. Well, we can't minimize this on a classical computer anymore. Okay, quantum chemistry, condensed matter physics, solid state physics. Here you have electrons that are coupled by different coefficients, and we want to find the ground state energy of this molecule. Then we do the Jordan-Wigner transformation. This turns these creation and annihilation operators into sigma x, sigma y, sigma z. This leads to a Hamiltonian, for example, for the H2 molecule. Again, we have four-body interactions that have to be quadratized. So for that, you can always refer to my book on quadratization. This is a bigger molecule. I'm probably running out of time, so I'll probably leave the rest of the time for questions. I'll just say that this is Microsoft's quantum team. It's called Station Q at Microsoft Research. This is the quantum station at Microsoft, where they're working on quantum computers. They talked about elucidating reaction mechanisms on quantum computers. This molecule, it's known as one of the most complicated enzymes in the world. Some people say it's the most complicated enzyme in the world. The carbon atom, usually carbon is coupled to 4 different atoms. Here it's coupled to 6 atoms. Okay, it's a very complicated molecule. And what this molecule does, it's an enzyme. It does nitrogen fixation at ambient conditions. That means room temperature, 1 atmosphere pressure. The way nitrogen fixation is done right now is through the Haber-Bosch process. This is done at 700 Kelvin temperature and 150 atmospheres pressure. This is consuming right now 2% of the world's energy supply. Okay? If we can understand how bacteria are doing it with this enzyme at room temperature and 1 atmosphere, we can save 2% of the world's energy supply. So that's why we want to understand this molecule. But solving the Schrodinger equation to find the ground state energy, for example, on this molecule is too hard on a classical computer. So these guys at Microsoft, they say that they can do this with 111 qubits. Okay, in 130 days with 111 qubits, they can find the ground state of this molecule. We actually did it in January 2019 on a classical computer, but we used a lot of cores for this. So this one we did in with Cyrus Umrigar at Cornell University and Garnet Chan at Caltech, California Institute of Technology, and Junhao Lee at Cornell and Jundong Lee at Caltech. So we actually did this calculation, but there's still more to do in that regard. So I'll just end off by saying that there's opportunities for collaboration. If you're interested in running calculations on quantum hardware, I get about 100 QPU hours per month on the DWave 2000Q. I have a lot of QPU hours available on the IBM machine and on Righetti's 8-qubit machine. Alternatively, IBM's 5 and 6 qubit machines are available to the public. I believe Alibaba, the Chinese company, has an 11 qubit quantum computer open to the public, although I don't have experience with it. I have a lot of experience with compiling problems. If you want to factor a number or you want to find a Ramsey number, computer vision, quantum chemistry, whatever it is, you have to turn the problem into an optimization problem. That optimization problem will have degree 4 terms, degree 5, cubic terms, degree 4 terms. You have to quadratize those into quadratic terms at the expense of adding auxiliary qubits. And then the connectivity between these quadratic terms those might not be perfectly embedded onto the hardware's graph. So then we have to do graph embedding, which is again something that my group is an expert at. So if you do want to run calculations on hardware, we can help. You probably know how to do it on hardware, but you might be doing it with more qubits than you need to. You might be doing it with 1,000 qubits. We might be able to do it with 800 qubits because we can save some auxiliary qubits by using more sophisticated quadratization algorithms. So with that, I thank you very much for your attention. Terima kasih. This is my email address if you wanted to ask questions. It's nikkei@hpqc.org, High Performance and Quantum Computing Research Lab.
Okay, thank you very much, Dr. Nikkei, for the very inspiring lecture, fascinating issues. And I can hear some of you start typing on your keyboard to ask some questions. I'm going to start with how far away are we? We can do computers that can do thousands of qubits, basically becoming a small computer. How many do you need before they start being useful for the kinds of problems we're talking about? How far away do you reckon that is?
It's a very good question. It's a very, very good question. I did mention, I think I mentioned somewhere here, when I started talking about quadratization, I said, if you want to factor a number that is hard for a classical computer, right now, the best estimation that we have, well, this was in 2017 that we did this work, but we estimated 5.5 billion qubits on a DWave machine if we want to factor the number RSA-232. At that time, in 2017, this was a number that had not yet been factored on a classical computer. So if we could factor this, if we could find the ground state of this Hamiltonian on a DWave machine with enough qubits, then we could do something on a quantum computer that a classical computer is not possible, is not capable of doing. Now this might be less than 5 billion. This might be maybe 1 billion because we have the Pegasus graph now. The Pegasus graph, it has a lot more connectivity. So going from 2 local to Chimera, 2 local to this is 2 local to Chimera, it's 5.5 billion qubits. 2 local to Pegasus, maybe 1 billion qubits. Then there's also better quadratization methods. So instead of needing 18,000 qubits to quadratize a 6,000 qubit Hamiltonian, maybe we only need 15,000, and then this 5.5 billion is roughly the square of this. So 15,000 squared. I don't know what it is, but it's going to still be billions of qubits. And that is also true even on circuit-based quantum computers, because it's true that with 72 qubits, you can get what some people call quantum supremacy. The classical computer is no longer able to model the quantum computer. However, to solve a real problem, like Shor's algorithm will need 1,000 qubits to factor RSA-232. But then the quantum computer is making errors. The quantum computer thinks that it's doing the NOT gate, but it's actually doing the NOT plus some error epsilon. And to correct this error, you now need a bunch of auxiliary qubits. So to actually factor RSA-232 on a circuit-based quantum computer with a circuit-based quantum computer, if it's 1,000 logical qubits, it might be 1 billion physical qubits. So I would say roughly 1 billion qubits. When we get to 1 billion qubits, then we're really going to have some powerful devices. However, the number of qubits is not the only thing. The error rate, how often is the quantum computer making errors? Because the engineering is still not perfect. Okay, until the engineering is perfect, and it never will be. It's always getting better and better. The error rate is a big deal. So it's not just the number of qubits, and it's not just the error rate and the number of qubits, but it's also, let's see if I have it here. It's also the connectivity between the qubits. So the graph connectivity, if we can get more, so here, this is a substantial improvement over the Chimera graph, because now we have couplings between Chimera cells. However, it's still not a complete graph. So this qubit over here is not connected to this qubit all the way over there. It's not connected to that. And because of that, because we want to solve a problem with 500 variables connected in a certain way, and the hardware doesn't have those qubits coupled in that exact same way, we have to introduce auxiliary qubits. So now this one and this one, two physical qubits have to represent one, oh, actually not this one, it's this one and this one. And so this one, if I want this qubit to be coupled to that one, then this one and maybe what's that coupled to? That's coupled to this. Okay, so these two are going to be, these two physical qubits are going to be one logical qubit. Now this one is connected all the way here to here. So I'll have 3 physical qubits for 1 logical qubit. That's a waste of hardware. If we can get, we don't just need more qubits. And what DWave was doing was they just kept making more and more qubits, but they didn't change the graph. So it was more and more qubits, but in the same pattern. What we need is maybe not necessarily more qubits, but more connectivity, because if we have more connectivity, then we can solve more complicated problems, even if the same number, even if we have the same number of qubits. So the answer is that maybe we need 1 billion qubits, but it's number of qubits is not the only metric to think about. It's also error rate. It's also the temperature at which they have to run. And it's also the graph connectivity.
Okay, thank you. We got a question from one of the students, Muhammad Trinur. How do we know the dot pattern point to? How do we know the dot pattern the same relation for the Pegasus and the Chimera Graphs, and why Pegasus be a fundament for this topology? I think it's more or less on how do we choose one of the gadgets for the graphs. Probably there's some considerations on why the existing computers put more emphasis on adding more qubits rather than creating completely new graphs, for example. Can you comment on that?
Yeah, so is there a question about the Pegasus graph here?
How do we know the dot? He said, how do we know the dot pattern in point 1, 2, 3, 4 has the same relation for the Pegasus and the Chimera graph?
How do we know that the relation in 1, 2, 3, 4? Oh, how do we know that these 4 have the same graph connectivity?
I think what I understand from his question is how do we verify probably that the graph in the Pegasus and the Chimera are analog?
Okay. Well, this is actually something very difficult, because in 2018 at the AQC conference, which happened at NASA in California, DWave presented a slide where they just showed this. They said, this is Pegasus. And they just showed that. And no one really knows what's actually going on here until you've actually worked out the graph, so the rules for how the qubits over here are connected was something that I worked on with Szilard Szalai and Nicholas Chancellor. And the 3 of us, we stared at, so this is what DWave showed. DWave just showed this slide on one of their presentations. They just had a bunch of lines going like this and like that. And what we did, Szilard Szalai and Nicholas Chancellor, we reverse engineered the Pegasus hardware and got a set of rules for how these qubits are coupled in Pegasus. We published it. It's an open source paper. You can see this on Archive. It's called Pegasus, and it tells you the exact rules for how to connect the qubits in the Pegasus graph. Now Chimera, this is very simple. Like you don't need any reverse engineering. This is just the graph K44. K44, that's the complete bipartite graph. So this is 4 qubits, 4 qubits. These are all connected to those, and those are all connected to these. And there's just K44 multiple times, and then the K44s are connected to each other. That's very simple. Here in the Pegasus, we actually have a Chimera layer. So these 4 unit cells form one Chimera layer. And then these 4 form another Chimera layer. Okay? That's the correspondence. So we have these 4, and then there's another 4. This is another Chimera layer. And it turns out that then it just repeats. So the next layer is actually connected all the way back to this. The next one is connected to this. And it took us a long time. It took us the whole summer to reverse engineer this hardware. And we managed to figure out that all the Pegasus graph is just 3 layers of Chimera graphs that are then connected by a bunch of K22 graphs.
Okay. We got another question from the audience. Some people obsessed with what happens when we have a quantum computer that can break pretty much all cryptography is gone. Do you see that as soon as we have enough of a working quantum computer, does the entire world suddenly becomes insecure for a period of time?
I don't think that is true, and I will tell you the reason why. Let me get back to the RSA cryptography section. So RSA cryptography, invented by Ronald Rivest and Leonard Edelman and Shamir. This algorithm from 1977, it's still being used right now, meaning that a lot of our information, our financial information, for example, if we do online banking, a lot of that information is secured using the RSA algorithm. And the being able to factor big numbers makes it possible to break the RSA crypto system, and therefore you can read Hillary Clinton's emails, for example. You can break codes. Now, there's a few things that can be done about this. Number one is that if the quantum computer can factor a number with 1,000 digits, like RSA 1000, it's not going to be able to. Right now, classical computers can only factor about RSA 230, maybe RSA 240, maybe a little bit bigger than that. Certainly, RSA 300, which is 300 digits, that cannot be factored on a classical computer. Now, let's imagine that a quantum computer can factor a number with 1,000 digits, okay? And that's the most that a quantum computer can do. Then, instead of using RSA 1000, we can use RSA 1 million, okay? And then a quantum computer is going to have a quantum computer needed 1 billion qubits to do this. Now it's going to need even more qubits to do that. And then it will take more time for the quantum computer to catch up. However, if you had 1 billion digit number for RSA, that means that it will be slow. So the classical computer will have to do a lot of information processing every time you send a transaction or something like that. However, RSA crypto system can be replaced by something called elliptic curve, okay? Elliptic curve cryptography. And with elliptic curve cryptography, the size of the key for which it's too hard for a quantum computer, elliptic curve cryptography can also be broken by quantum computers by doing discrete logarithms. But it would be harder because the key size, instead of needing 1,000 digit number as your key size in RSA, in elliptic curve, you might only need a 200 digit number. So the difficulty, however hard it is for a quantum computer to factor this, it will probably be equivalent to just as hard to factor a number of to hack an elliptic curve crypto system using this many digits. Now, elliptic curve and RSA cryptography are what people call pre-quantum cryptography. There's also something called post-quantum cryptography. Post-quantum cryptography. Okay, now this is cryptography that is secure against, it's secure against quantum computers. Okay, quantum cryptography, or if your quantum computer is strong enough to factor this number, then your quantum computer is also strong enough for quantum cryptography. So your cryptography will be quantum as well. Or you can have, there's certain post-quantum cryptography algorithms on classical computers. So it's not even a quantum computer. A classical computer can do post-quantum cryptography. One example was invented by a professor at University of Waterloo named David Zhao. And this is called isogeny-based, oops, I just want to finish writing his name, David Zhao. Okay, and he has come up with a method called isogeny-based quantum cryptography, or sorry, isogeny-based post-quantum cryptography. This is safe against there's no quantum algorithm that can hack data that has been secured using isogeny-based cryptography. There's also another cryptographer by the name of Daniel Bernstein, and he's come up with a lot of different methods which are secure against quantum computers.
Okay. We got a basic question from a student, and this is quite popular, I believe. This is a question about quantum entanglement and the effects that we see there. Because we can separate, because of the entanglement, we can separate two photons and see the same effects on both. Are we likely to be able to use that as a means of communications? Can we affect one and see the effect on the other?
Yeah. Yes, there is something called, I don't know why I removed this. I just wanted to make more space to draw. Let me get this. Okay, so if we have an entangled state, like basically 0, 1 plus 1, 0, all multiplied by 1 over the square root of 2. This, you're asking if this can be used for quantum communication. And the answer is somewhat yes. Yeah, there are some protocols such as QKD, which stands for quantum key distribution. And there's another one called quantum teleportation. Quantum teleportation is where we have some qubits. Alice has some qubits, and Alice wants to send those qubits to Bob. Okay, and this would not be possible on a classical computer because qubits have an infinite, a lot more information than classical bits do. However, if Alice and Bob share an entangled pair of qubits, then it's actually possible for Alice to basically teleport this data to Bob. So that's a method of communication of whatever information Alice has can be sent to Bob through, and entanglement is important for that to be possible. Some people talk about sending information faster than the speed of light because of entanglement, but that I'm not going to say that that is true. I actually answered this question for someone on, I wrote a long answer about this on one of the Stack Exchange, on the Space Stack Exchange. Maybe I'll find that later and then send it to you if you're interested.
All right.
I can take the next question.
Yeah. So we got another question. Does quantum communication needs quantum computing? So sometimes quantum technology is comes in various form, right? And many people think that quantum communication and quantum computation are the same thing, and maybe you can shed some light on that. I believe they're different, but they're in somehow related to each other.
Yes. Okay. So quickly, I'll just say I found quantum technology for Starship communications. Someone is asking here that based on quantum entanglement principle, can you send information faster than the speed of light or something like that? And I actually answered that question here. Okay. So I wrote this answer saying that the qubits are entangled, and I'm explaining what entanglement is, and I'm explaining why I don't think that you can send information faster than the speed of light. Because there's wave function collapse and there's a lot of other things. I've written a lot of details about that there. So the next question now was about quantum communication versus quantum computation. That's a good question. So, okay, now I don't need this anymore. I'll just maybe use something where I can type faster than using the mouse. So, I'll make bigger text. Let's make this 36. So you're talking about quantum communication, right? Quantum communication is sending quantum information to other people. Quantum computation, I would say this is computing things. Like I want to compute the solution to a differential equation, or I want to compute the eigenvalues of a matrix. Okay, that's quantum computation. There's also another thing, quantum metrology. This is using quantum mechanics to make measurements. So examples would be, for example, a quantum thermometer. This is to measure the temperature, but you know, you're measuring the temperature, it's 52 degrees Celsius or 35 degrees Celsius. Sometimes you get that the temperature is 35.12 degrees Celsius. But what if you want to measure that the temperature is 0.00000001 degrees Celsius? This you can't do with a classical measurement device. But using entanglement between the molecules that you're measuring the temperature of and the measurement device, you can actually do quantum metrology, which is a third thing. And all three of these things fall under quantum information, okay, or quantum engineering. This is the design of technologies that use quantum information. So quantum computation. Now, in quantum communication, you might have to do a little bit of quantum computation. Like you might have to do a Hadamard gate and a controlled NOT gate if you're sending information to Bob. Or to read the information, you might have to do a little bit of computation. But that's the same, like if I'm communicating to you, I'm sending you an email, that's classical communication. But it was done with the help of a classical computer as well. So it's a good question. And basically the distinction between communication and computation, it's the same as it would be anywhere else. Communication means sending information to someone else. Computation means calculating something.
Okay, I think we still have time for one last question. Okay, I have a question. So given that this new paradigm in quantum technology, do we need new maths to go along with the new hardware? Are we seeing the evolution of a new maths in the same way that classical computing is based on algebra, probably? Maybe you can come comment on
yes. Yes, there is new mathematics that was built. So it's yes and no. There's a lot of new mathematics that you need to learn in order to do quantum computation. To understand Shor's algorithm, you have to understand the quantum Fourier transform, and you have to learn how to work with qubits. But it's the mathematics of quantum mechanics. So it's the same mathematics that you would use to model a system quantum mechanically on a classical computer. I don't know how else to describe that. So the mathematics, like if you're familiar, there's this Dirac notation, and there's the concept of a tensor product, and the concept of a partial trace. So not the trace of a matrix, but tracing out part of the matrix. So I have a density matrix of both Alice and Bob, and I trace out Bob's qubit. So that's an example of mathematics that we use in quantum computing that we don't use so much in classical computing. And then when we want to actually do quantum information, we have stabilizer codes. I can't type that fast. Stabilizer codes. These are basically, but the thing is, this mathematics exists in the form of group theory and representation theory. So this mathematics does exist elsewhere. And also, there's category theory. That's another area of mathematics that is used a lot in quantum computing to think about quantum information. But category theory also existed before quantum computing did. A lot of this mathematics that we're using for quantum computing, yes, it is being developed a little bit more now that quantum computing is interesting. But all of this mathematics, it's the same mathematics as we were using before when we were studying quantum mechanics of a 50-particle system. It's now that instead of just 50 particles, those 50 particles are now qubits. We're calling them qubits, but before we called them particles. So the mathematics we need to model 50 particles, it's still the same. Whether it's 50 particles or 50 qubits, we're still modeling quantum mechanics using the same mathematics.
All right. Thank you very much for the explanation. I think we're short on time, so I will conclude this lecture. We have seen a very enlightening, thorough explanation on quantum technology, quantum computing, and algorithm in particular. Also on integer factorization and discrete optimization. And with that, I thank Dr. Nike Dattani for giving us the lecture this morning. And also thank you for all the audience for your participation on this guest lecture on compiling your calculation to run on quantum hardware. Hopefully this lecture will inspire you, especially students, to become more engaged in quantum technology related research. And hopefully you can develop quantum technology in Indonesia as well. With that, I conclude this lecture. Thank you, and see you again in the next guest lecture. Thank you very much.
Thank you, Dr. Nike.
Thank you.
Thank you.